Morning, everyone. Welcome to the lecture for Math 60. We are covering section 3.8, which is solving equations involving fractions, right? Or rational numbers, if we want to use the mathematical term. So we're going to start with the review, but even before I get to that, I want to remind you all that this class kind of has two parallel tracks. On the one hand, we solve equations, and on the other hand, we learn number operations. And so far, all of chapter 3 has been learning number operations. How do you multiply, divide, add, and subtract fractions? Whereas earlier chapters, there was, solving one-step equations or solving two-step equations involving integers. And so this chapter or this section puts together solving equations with number operations. And so I'm just going to review basically all of these pieces because I know it may have been a while since you've thought about, okay, now how do I solve equations again? So solving equations. I'm just going to do a bunch of examples demonstrating some different things. So maybe a real simple example to start, x plus 7 equals 20. In general, to solve equations, we want to isolate the x by using the opposite arithmetic. So if it's x plus 7 equals 20 and I want to isolate the x, I'm going to subtract 7 from both sides. And I get x equals 13. Lots more examples. What about x minus 8 equals 24? Well, since I'm subtracting 8, I want to use the opposite arithmetic operation. So add 8 to both sides and I get x equals 32. Sometimes you get the x as a negative. And we can approach this a couple different ways. One way is to say, well, I don't want the x to be negative, so I'm going to add x to both sides. And I get 7 equals 10 plus x. And now I'm back where I was in the first example. Things are just written in a different order. And I subtract 10 from both sides, and I get negative 3 equals x. That's one way to do it. The other way is to say, I don't care that the x is negative. I'm still going to use my minus 7 on both sides to isolate that x, and I get minus x equals negative 3. And so if negative x is negative 3, oh, that's positive, sorry. 10 minus 7 is 3. If negative x equals 3, then x equals negative 3. So these three examples are versions of one-step solving equations involving involving specifically addition or subtraction. And then we also looked at, well, how do you solve equations that involve multiplication? So 2x equals 22. We want to clear any coefficients by dividing. So the 2x, we clear the 2 by dividing by 2, and we get x equals 11. If my coefficient happens to be negative, like negative 7x equals 35, I just divide by negative 7. And I get x equals negative 5. So those are one-step equations involving multiplication. I could have an equation that starts off with the division, x divided by 4 equals 3. So we want to clear the division by multiplying, because multiplication is the opposite arithmetic for division. Multiplication undoes division. So I'm going to multiply both sides by 4, and I get x equals 12. So these are the one-step solving equations. We can have two-step equations. Like I could have 3x minus 1 equals 14. And we want to isolate the x terms. And we'll do that by adding 1 to both sides. And I get 3x equals 15. And then we want to clear the coefficient by dividing both sides by 3. And we get x equals 5. And we can have different versions of two-step or multiple step equations. So far, I've been using all integers, right? Because I'm reviewing the process, and then I'll do a quick review of arithmetic with fractions, and then we'll put those together. But let's do another example. Let's look at x minus 4 divided by 5 equals 2. And in this case, let's clear the division first by multiplying both sides by 5. And that gets me down to x minus 4 equals 10. And now I'll isolate x by adding 4 to both sides, and I get x equals 14. And then we talked a little bit about some of our number operations, in particular how to distribute, and we included that. We were able to have more complicated equations like 2 times x plus 7 equals 24. And this one, we can also solve it a couple different ways, but in general, if your x plus 7s are all, if your x plus 7 is a parentheses, first I'm going to clear the coefficient by dividing both sides by 2. And I get x plus 7 equals 12. And now I'll isolate x by subtracting 7 from both sides. And I get x equals 5. All right, anybody have questions about that review there? Okay. Let's do a quick review of arithmetic with fractions, and then we're going to put these all together. Review of arithmetic with fractions. Let's take as an example 4/3 times 7/5. So multiplication, that tends to be the easiest because you just multiply the numerator, you multiply the denominators, and you build your new fraction.
There's 3 and 4.
Yes. Sometimes the multiplication ends up with some cancellations when you do the multiplication, like 12 times 15 over 5 times 36. You can do the reduction before or after. So let's do them 2 ways. I kind of like the before. 12 divided by 36. Notice I've got a 12 and a 36 here. That is actually equal to 1 and 3. And the 15 is actually equal to 3 and 1. So this whole thing is 3 over 3, which is 1. But that's okay. We don't have to do it that way. We can do our other multiplications. 12 times 15 over 5 times 36 equals 180 over 180. That equals 1. That was not my original intention to get a multiplication that simplified all the way down to 1, but so I did. And in fact, that's kind of useful information because there was something else I wanted to talk about. This means that 12 over 5 and 15 over 36 are reciprocals because they multiply to 1. And it's probably a little bit easier if we write the 15 over 36 as 3 times 5 over 3 times 12, and then we can see, yeah, for sure. 15 over 36 is the same as 5 over 12. And now I can see how it's just a flipped fraction. And reciprocals are going to be one of our biggest tools for solving equations with fractions. Okay, multiplication taken care of. Let's look at division. 2/3 divided by 4/7. When we want to do division, you multiply by the reciprocal of the dividing fraction. 2/3 divided by 4/7, and I can write it vertically also. Is the same thing as 2/3 times 7/4, which is 2 times 7 over 3 times 4, which is 14 over 12, which is the correct answer. It's not the reduced answer, though. It reduces to 7 over 6. And one more example. Let's look at 15 over 8 divided by -7 over 3. That's another way. Sometimes you write fraction divisions. There's so many different ways. So again, we want to multiply by the reciprocal of the dividing fraction, 3 divided by -7, instead of -7 divided by 3. And that allows us to do the multiplication across the top and across the bottom. All right. So let's look at addition. Let's look at 3/2 plus 5/2. Well, if the denominators are the same, you get to just add the numerators over the same denominator. 3/2 and 5/2 is 8/2, which is the right answer. It is not reduced, though. It's also equal to 4. And if you're trying to add fractions that don't have the same denominator, like 7/3 plus, let's see, 19/6. Your first step is to change them so that they do all have the same denominators by figuring out what's missing from each fraction. 7/3 plus 19/6, 19 over 6. The 7/3 is missing a 2, which gets the denominator to be equal to 6. The 19 over 6 isn't missing anything. So it becomes 7 times 2 over 3 times 2 plus 19 over 6, which is good because that's 14 over 6. plus 19 over 6, which is 33 over 6. I should do one more step. 14 plus 19 all over 6, which is 33 over 6, which is the right answer, but it's not reduced. It's also equal to 11 over 2. Okay. Any questions so far? Subtraction of fractions, exact same idea, except once you get them over the same denominator, you subtract. So let's do, as an example, 23 over 8 minus, I'm just gonna start over. Sometimes when I'm tired, I have less patience with myself. Yeah. Okay, let's do 23 over 8 minus 17 over 11. So here I'm subtracting. That's not what's really new. That's not the important part. The more important part is the least common multiple of the denominators, which the book actually calls the least common denominator, which is fine. If 8 and 11, so if the denominators don't share any primes, then the least common multiple of the denominators is just the product, the result of multiplying them. The reason we spent so long, besides the fact that it's interesting, but the reason we spent so long looking at prime numbers is because it helps us when we're working with fractions, whether we're reducing fractions or adding fractions or subtracting fractions. Understanding how numbers are built from primes really helps us when we're doing division. So in this case, 8 and 11 don't share primes because 8 is 2 times 2 times 2, and 11 is prime all by itself. So the least common multiple of 8 and 11 is 8 times 11, it's 88. We don't have to do more work. So that means that 23 over 8, what's it missing? Right, it's missing the 11, so it's missing 11 over 11. And 17 over 11, what's it missing? The 8. Because that's what's going to get them to have the same denominators. So I have 23 times 11 over 88 minus 17 times 8 over 88. Some of this I can do in my head, 253 over 88. I don't expect you to do that in your head. That's okay. There's a cool trick when you multiply by 11. I can show you another time. 17 times 8 is 136. And now that they have the same denominator, I can just subtract the numerators. And let me do a little bit of side work over here just to organize my subtractions and to help remind you all how to do subtraction by hand. 253 minus 136. Make sure everything's lined up. And then we subtract vertically. 3 minus 6. I would say I can't do that because 3 is smaller. So I'm going to borrow one of the 10s from the 50 part of it. And 13 minus 6 is 7. 4 minus 3 is 1. And 2 minus 1 is also 1. And I get 117 when I do that subtraction. So this equals 117 over 88. That is the right answer. We don't know if it's reduced yet. So this is the right answer. It will reduce if, and again, we wander into prime territory, if 117 and 88 share any primes. And if I weren't doing the review, I'd go through this in more detail, but I tell you they don't share any primes. So in this case, they don't. So 117 over 88 is already reduced. One more example, and then we'll put the two ideas together, solving equations with fractions. Let's subtract 13 over 12 minus 5 over 21. They don't have the same denominator, so I want to find what's missing. Now I could do 12 times 21. That's okay. That's less work on the front, but it's going to make more work on the back end. So instead, we can find the least common multiple of 12 and 21. So that when we find our equivalent fractions, it's a little bit less work. So the way I do this is I count by 12s, 12, 24, 36, 48, 60, 72, 84, 96, etc. And in parallel, count by 21s, 21, 42, 63, right? Yeah, 63, 84. And as soon as you see the same number appear in both, that's the least common multiple. That's the denominator I'm going to be going for. And to figure out what's missing, count the number of multiples of 12. 1, 2, 3, 4, 5, 6, 7. I know those numbers are super small. So that means the 13 over 12 is missing a 7. Because 12 times 7 gets me to 84. And the 5 over 21 is missing a 4 because 21 times 4 gets me to 84. I did a little bit more work on the front end, but my arithmetic's going to be easier at this point, right? Because 13 times 7 is easier than 13 times 21. So I get 13 times 7, which is 70 plus 21, which is 91, which is probably the most prime looking number that's not actually prime. I think it's like, wow, 91's not prime. That always surprises me. And I know the bottom has to be 84 because that's exactly what I built to. And then it's going to be minus 20 over 84. And I get 71 over 84. And I have to ask myself, does that reduce? It will reduce if they share any primes, but I'm here to tell you that 71 itself is a prime, so it doesn't reduce. So these last two pages that I put together, the review of fractions, like I said, it's a summary, and the way I've observed you all taking notes, I'm sure you have much more extensive notes from the past 2 weeks. But these two pieces right here, these 2 pages of notes, are going to be really useful as you start working through equations that involve fractions, because it'll be a reference on, oh, what do I do now? How do I do this, etc. So let's put it all together and look at equations involving fractions. Let's start with x plus 7/3 equals 19/3. So I need to integrate the how do I solve an equation with how do I do arithmetic with fractions. So how do I solve this equation? I want to isolate x. How do I isolate x? By what? What coefficient? Oh, but that's not a coefficient because it's not actually multiplying by x. This is x plus a number, right? So you have to see this, and I appreciate that. You have to see this as x plus a number. Even though that number is a fraction, it's just a number. So how do you isolate x when you add a number to it? You subtract the number. Just in this case, what we're going to be subtracting is a fraction, but that fraction is still a number. So it's x plus 7/3 equals 19/3. So I just have to subtract the 7/3 from both sides. That cancels out the 7/3 on the left, and I have 19/3 minus 7/3. And so now I check my reference sheet about how do I subtract fractions if they have the same denominator? Just right across, 19 minus 7 all over 3, which is 12 over 3. That's my answer, x is 12 over 3. Can I reduce that fraction though? Yeah, that's also the number 4. So x equals 4. So one of the big challenges is when you're working with fractions, things that used to be clear, if I said that x plus 7 equals 19, you would know for sure that you subtract the 7. But now that it's a fraction, it can be harder to pick out what are the operations that I have to undo. All right, let's do another one. Let's look at x minus 12/7 equals 22/5. So what do I want to do in this equation to solve for x? Exactly, I want to isolate x by undoing the subtraction. So I'm just going to add the number, which is 12 over 7. I'm going to add that number to both sides, which cancels the negative 12/7 on the left and gives me 22 over 5 plus 12 over 7 on the right. And now I go to my fraction reference sheet and I say, how do I add two fractions when they have different denominators? I find the least common multiple, I make them have the same denominators. Since 5 and 7 don't share any primes, I can just find the least common multiple of the denominators by taking the 5 and the 7 as the missing pieces. (22 times 7 is 140 plus 14, which is 154. 5 times 7 is 35. And I'm going to add to that 60 over 35 because 12 times 5 is 60. I'm going to get 214 over 35. If you notice me getting my arithmetic wrong, please catch me, because yeah, I do that all the time. This is the answer, that is X. I don't know if it reduces. It'll reduce if there are any shared primes. Well, 35 is 7 times 5. So let me just check 214 divided by 7, just in case. Nope. It doesn't divide evenly. And since it doesn't end in 5, I know it doesn't divide by 5. So my answer is X equals 214 over 35. When we solve these equations with integers, usually you'd get an integer and you could kind of look back and be like, yeah, that makes sense. But what this equation is saying is that 214 over 35 minus 12 over 7 equals 22 over 5. I definitely can't just look at that and tell you, yeah, that makes sense. Right? It's a lot harder to check equations with fractions than if they were just numbers. But we still could, right? You'd have to do your fraction arithmetic. You'd have to get the 12 over 7 to be something over 35. And then when you do the subtraction, you would be able to get that it ends up reducing with 22 over 5. I'll do it this time. I probably won't do it every time. I know that to get from 7 to 35, I need to multiply by 5 over 5. So it's 214 minus 60 over 35, which is the 154 over 35. And then I have to see, can I reduce that? Because it certainly doesn't look like 22 over 5 yet. But if I reduce it, it does in fact turn into 22 over 5. So checking is not as straightforward a process when you're working with fractions as it is when you're working with integers. Okay, so we have done one-step equations involving fractions, x plus 7/3 and x minus 12/7, and those involved addition or subtraction. So now let's do one-step equations that involve multiplication or division. 3/7 x equals 19 over 2. What do we want to do in this question?
Right.
Yeah, we want to clear this coefficient. By division, right? We're going to divide the whole fraction. But when you're working with fractions, actually we want to multiply by the reciprocal, because that's what division by fractions is. We want to multiply by the reciprocal of the coefficient. So 3/7 x equals 19 over 22. The coefficient is 3 over 7. So what's its reciprocal? Exactly. In this case, we just flip the fraction, 7 over 3, and we make sure we multiply both sides by that 7 over 3. Then the 7s on the left cancel, the 3s on the left cancel, which gives me the x that I was looking for. And now I go to my reference sheet to remind myself, how do I multiply two fractions? I just get to multiply the tops and multiply the bottoms. And I found x, which is 19 times 7 over 2 times 3, or 133 over 6. Again, I might ask myself, does this reduce? Well, this one doesn't, because 19 is prime and 7 is prime. 2 is prime and 3 is prime. So the tops and the bottoms don't share any primes. So it doesn't reduce. Just like with the arithmetic itself, solving a one-step equation with fractions is easier when it's a multiplication, because it really is just a multiplied by the reciprocal. And you won't see something like this: x divided by 2/3 equals 4/7. Nobody ever writes that. So when we're doing these examples, I'm not going to say x divided by 2/3. I'm going to say 3/2 x equals 4/7. So we had an example of addition, we had an example of subtraction, we have examples of multiplication. You don't see a inline division by fractions. That's just not how it's done. Well, probably I can't say never, but I would be surprised. So let's solve this one. It's similar. 3/2 x, so we want to multiply by the reciprocal of 3/2, which is 2/3. And we want to make sure we do that on both sides. And we get x equals 4 times 2 is 8, 7 times 3 is 21. No shared primes, so we're done. Let's do one more example where we're going to have to reduce. Negative 9/8 x equals 6 over 40. We want to clear the coefficient, so we want to multiply by the reciprocal. What's the reciprocal of negative 9/8? 8 over negative 9. Yep. And you can think of that as often we just write it as we don't care where the minus sign goes, because a minus is a minus. Regardless, the 9 and the 9 cancel, the 8 and the 8 cancel, and the minus times the minus cancels, which gives us the x on the left. And then 6 times negative 8 is negative 48. And 40 times 9 is 360. I multiply the numerators, I multiply the denominators. I'll do one more step. 6 times negative 8 over 40 times 9, which is the correct answer, but this one can probably be reduced because it's going to share primes. And you can do it prime by prime, but sometimes you can also look at it and say, aha, I can think of a couple numbers that divide the top and the bottom. For example, 12 divides the top. 12 times negative 4 is negative 48. And 12 divides the bottom, it's just 12 times 10. Oh, sorry, 12 times 30. And so those 12s cancel, and I get negative 4 over 30. And I say, oh, I can go one more step because 4 and 30 are both even, and I get negative 2 over 15.
From the negative sign went from the 9 to the 8.
Because I got lazy. Yeah, so that's a good question. Let's do a quick review of negative fractions. -9/8 is the same as 9/-8, which is the same as negative in front of 9/8. Those are all the same. So when I flipped it, I left the minus in the top.
Okay.
Which is pretty typical. It's still a reciprocal because when you multiply them together, you still get 1.
Okay.
Yeah, so it's pretty typical to, if you have the minus in the top and you flip it, you leave the minus in the top.
Okay.
Yeah, because it doesn't matter mathematically. And it's more common to have a negative in a numerator than a denominator, just in terms of our mathematical punctuation.
Thank
Yeah. All right, so now let's do a two-step. Let's solve 2/5 x plus 1/3 equals, it probably doesn't matter what I end up doing, 7/10. Let me actually see what the book, because there are a couple different ways to approach this. Wow, that's really weird. It's almost exactly one of the ones from the book as an example. Huh. Okay. I'm gonna show you two different ways because I want you to pick the way that you like better. First, we're gonna do it in a way that's very analogous to how we solved them when they were integers. We want to isolate x. So what's our first step for isolating the x? Now if these were numbers, that'd be a number times x plus a number. And so we would start by getting rid of the plus number, right? Isolate x by undoing the addition. And I'm not saying that's wrong. I think that's the other way, Jesse. So we're gonna undo the addition by subtracting 1/3 from both sides. And we get 2/5 x equals 7/10 minus 1/3. And now we use fraction arithmetic to find a least common multiple of the denominators. In this case, I think it's going to be 30 because 10 is built from 2 and 5 and 3. They don't share primes. So 2/5 x is going to be, to get to 30, my 7/10 is missing a 3. And to get to 30, my 1/3 is missing a 10. You see how what used to be pretty straightforward with integers, you just subtract. Now involves a lot more arithmetic as part of that step. That's the added complexity of working with fractions. Nevertheless, we do have all the tools, and with your reference sheet, that's going to be 21 minus 10 all over 30, which is 11/30. Okay. All right, as long as you follow all those rules of fraction arithmetic, we have now successfully isolated the x and simplified the right side. And now we are back at solving an equation that involves multiplication by a fraction. So now we want to clear the coefficient. And how do we clear the coefficient when it's a fraction? multiplied by the reciprocal of the coefficient. So the 2 over 5x, we're going to multiply by 5 over 2. And then we make sure we do that on both sides. You have to go slow enough to not to, you may not have noticed, but I got very close to making mistakes twice when I wrote this right side down, because I was writing a little faster than my brain could keep up with. So it pays to go real slow and methodically when you write your steps down, because there are so many of them. There's so many numbers when you're working with fractions compared to when you're working with integers. And now the 5s and the 2s cancel on the left, and so we have x on the left, and we multiply our fractions. 11 times 5 over 30 times 2, which is 55 over 60, which is the right answer, and also it can reduce because 5 divides into both 55 and 60. So x equals 11 over 12 is our answer. I'm going to check that really quick, because when I show you the other way, I want to make sure I get to the same answer. So let's do it. Okay, so my original equation, which you all can't see, is 2 over 5x plus 1 over 3 equals 7/10. So I'm going to put 11 over 12 in for x. This might be a time when you grab your calculator to make it a little faster. That's going to be 22 over 60 plus 1/3 is the same as 20 over 60. And 7/10 is the same as 42 over 60. And I can see that that works, because 22 plus 20 equals 42. Calculators are fine. I did this really quickly. I got them all over the same denominator, just in my head, which is a skill to work toward. But you're welcome to check with a calculator. All right, let me show you the other way. Which is usually fine. There are a couple times somewhere in the future where you could get into trouble. And you get to pick. So I'm looking at an equation that involves fractions, and I say to myself, I don't want fractions. Fractions are hard. I don't like fractions. So I'm going to get rid of all my fractions. And here's how I'm going to do it. I'm going to multiply 2 over 5x plus 1 over 3 equals 7 over 10. I'm going to multiply each of those terms by 5. What's that going to do to the 5 times 2 over 5x? Going to cancel. Boom. My x is no longer a fraction. Yes. 7 times 5 over 10 is 35 over 10, right? Yeah. And then I say, wait a minute, I still have fractions. I don't want fractions. So I'm going to multiply everything again. What am I going to multiply by this time? Yeah, the 5 got rid of the first fraction. 3 will get rid of the next one. So I multiply every term by 3. 3 times 2x is 6x. Now the 5/3 times 3, that's going to cancel the fraction. And 35 times 3 is 105. Calculators are fine. Nothing wrong with a calculator. Aha! I'm down to one fraction. How do I get rid of that last fraction? I'm going to multiply everything by 10. 10, 10, 10. And I get 60x plus 50 equals 105. This is an equivalent equation, right? It's in the same fact family, because the x that makes the first equation true is going to be the x that makes this bottom equation true. But this bottom equation doesn't involve any fractions. I've done more work on the front to do less work on the back. In math, you often get that choice. Do I want to do my work up front to make it easier on the back end? Or do I want to keep it easy at the beginning, right? Just by, right, adding and subtracting. I don't have to do a lot of extra work before I start solving for x, but the solution part is more challenging. And here, I haven't even started solving for x, but I went ahead and I made it simpler. It's like, you're going to work on your car. And so you can jump right in. I need my wrench, grab it, toss it away. Okay, where did I put my screwdriver? Okay, oh, now I need a new O-ring. Where's the O-ring? Right? Some people work that way, and that's great. Other people sit down and they lay out all their tools, and they have all their O-rings of all the different sizes. They have all their lubricants and oils, and everything's just like ready to go. And then they start working on their car. And other people, that's how those people do it. There's not a wrong way, there's a way that works better. And so this is that option. Now I can solve this using my rules without having to deal with fractions. And I get 60x equals 55, because 105 minus 50 is 55. And I divide both sides by 60. And guess what? This is the exact same fraction I got before, 55/60. I did more work on the front end. I laid all my tools out so that the actual work would be a little bit easier. And we still want to reduce this. It's 11/12. You are absolutely welcome to use this method every time you solve an equation involving fractions. You should still know how to add fractions together, how to multiply fractions together, etc., because that's an important skill in and of itself. But when you're asked to solve an equation, you get to decide how you do it. Okay, that wraps up this video. The worksheet just gives you opportunities to work on all of that.